In this section, let's see how we can create graphs in polar coordinates. Before we actually start graphing in polar coordinates, let's take a look at a simple but useful tool that will help us when we graph. Let's talk about symmetry. In algebra, you learn about symmetry with respect to the x-axis, with respect to the y-axis, or with respect to the origin. Here we have something similar. If an equation has a kind of symmetry, then you have that much less work to do when you're actually graphing. If you know something is symmetric with respect to a vertical line, then all you have to do is graph everything on one side, everything on the other side is automatic. If you know something is symmetric with respect to a horizontal line, same thing. You just need to graph the top and the bottom is automatic. So here, let's see what it looks like when we test for symmetry with respect to axes in polar coordinates. In polar coordinates, we're going to have two possibilities. We're going to have symmetry with respect to either the line, excuse me, the line theta is equal to 0. This is basically what we mean by the, when we say this, we basically mean the x-axis. Or with respect to theta equals pi over 2, by which we mean basically the y-axis. Okay, the way we're going to test it is going to be similar to the way we test for symmetry in algebra. We're going to replace variable or variables with the negative versions of themselves and see what happens. Oh, actually, I'm forgetting one. So with respect to the x-axis, the y-axis, we can also be symmetric with respect to the pole, just like we can be symmetric with respect to the origin in algebra. With respect to the pole. Here, when you're symmetric with respect to the x-axis, you can say you're symmetric with respect to theta equals to 0. There is another name for this one. This is called the polar axis. Okay, there we go. So now let's go and take a look at some examples. Okay, what I'm going to do is I'm going to test this equation for symmetry. And there's 3 different kinds of symmetry, which we'll test 3 different ways. Test, let's go with r equals 1 plus 2 cosine of theta for symmetry. So we're going to test 3 different kinds of symmetry. First, we're going to test with respect to the polar axis. Basically, what this means is everything above the x-axis and everything below the x-axis, which is also called the polar axis, are the same. Okay? To test for that one, all we're going to do is we're going to replace our angle theta from minus theta. So let's go ahead and put this in red. Here, this is going to be the x-axis. And here we're going to replace theta with negative theta. Okay? So the way this works is you take your equation and replace your theta with a negative theta. And then you're going to simplify by whichever means is appropriate to that equation. Here we notice that, cosine is an even function. And here cosine is even. And with an even function, you can just ignore negatives. So this becomes r equals 1 plus 2 cosine of theta. Because of an even function, you can ignore the negative. But now this is the same as the starting equation. This is the same as the original equation. What that means is that you have a graph, or rather you have an equation, whose graph will exhibit this kind of symmetry. So yes, we will have symmetry with respect to the x-axis. Now let's try the next one. Let's try the y-axis. We're still using the same equation. Let's test to see if you have symmetry with respect to the y-axis. In order to do this one, what we're going to do is we're going to replace both theta and r with their negatives. So we're going to replace theta with negative theta, and we're going to replace r with negative r. And we'll see what happens. Okay? So here we're going to take r equals. So now this r is now going to become a minus r. And we have 1 plus 2 cosine of minus theta. So that's our second test here. And here, because you have an even function, just like above, this negative can be ignored. But this negative can't be ignored. It's negating the entire expression. They say, well, multiply both sides by -1. Well, okay, that'll get rid of the negative from here, giving you r. But if I multiply by -1 on both sides, that makes this 1 into a negative. And that makes this 2 into a negative. And this is not the same as the original equation. This one's different. So here, you do not exhibit this kind of symmetry. So if you do the replacements and you end up with where you started with, then yeah, that symmetry is valid. Your function does, your graph would have that kind of symmetry. But if it's something different, however small that difference might be, then you don't have that kind of symmetry. The third one is we can be symmetric with respect to the pole. If we replace, my color coding has stopped. Oh well. We're going to replace r with -r. So here we're going to take this r, we're going to negate it, and everything else stays the same. And yeah, that's different. There's no reason to get rid of that r. Even if you try to get rid of the negative in front of the r, try to multiply both sides by -1, okay, that makes your r a positive, but again, it negates the other side, and that is, again, different from the original. So this symmetry is not exhibited either. So this graph would have symmetry with respect to the x-axis only, meaning that the bottom, whatever it looks like, would be the same as the top, something like that. I haven't actually taken the time to graph this, but you would have this kind of symmetry. You would not have symmetry with respect to the y-axis. You would not have the left side and the right side the same. And you would not have symmetry with respect to the origin, where you would flip across the origin, something like this. You would not have either of these, but you would have something like this. Okay? And again, that's because this result is different from the original equation. So what that means is if we were now to graph this, we would find that we only need to graph the top. The bottom would be kind of automatic. We would know already what happens because of this type of symmetry. So let's do that. For our next example, now let's go ahead and graph r equals 1 plus 2 cosine of theta. Now, just like in algebra, when you graph, you can do it the long and simple way, or you can do it the slightly more complicated but shorter way. In algebra, if you were graphing something like y equals x squared plus 5x plus 6, one way to graph this is simple. It's just kind of long. You could plug in x is equal to 0, x is equal to 1, x equals 2, x equals 3, x equals 4, x equals 5. Plug in about a dozen points, connect the dots, and you'll form your graph. It's a parabola. It's simple. You just have to plug in numbers, but it's kind of long. The other way to do this in algebra is you could say, well, it's a little shorter, but it's more complicated. I could find the vertex of this. I can either complete the square or I can use the formula. Either way, once I know the vertex, then I could solve this equal to 0, either using the quadratic formula or by factoring, and I would find the x-intercepts. And instead of plotting a dozen points, I could get away with 3 points, and I would graph the same thing. It would take me a lot less time, although it's more complicated. It takes more effort to do. Same thing will apply here. One way you can graph this is very simply, even though it takes longer. You're going to just plot point after point after point and connect the dots. We're going to do that first. Our first example will be done just like that. But then, in a little while, we'll see how to do things with a little bit more finesse. How to be a little more methodic. Okay, but for now, we're just going to plot some points. Okay, so I know that my graph will be symmetric with respect to the polar axis, the x-axis. So I don't really have to worry about plugging in numbers down here. I can get away with just plugging in numbers between 0 and pi. Or I can do 0 to 180 degrees. But here I'm going to use radians. Okay, so let's go ahead and graph this. All right, so just plotting some points. We're going to plug in theta, and that theta will tell us what r is. So, starting from 0, Cosine of 0 is 1. 1 times 2 is 2, plus 1 is 3. That's all it takes. I'm just plugging in numbers. If you really, really want to, you can just grab a calculator and have it plug in the number for you if you really like, right? Here, cosine of 0, make sure I'm in radians. Yeah. Cosine of 0 is 1, times 2 is 2, plus 1 is 3. Right. Either way. So now let me just plot a few more points here. Let's do pi over 6, pi over 4, and pi over 3, and pi over 2. And I choose those because I know those kind of just off the top of my head. Those are the ones from the unit circle. Now, of course, I could do pi over 17, pi over 9, and 2 pi sevenths, but I don't know those off the top of my head. I could grab a calculator for those, but if I know these already, why not just work with those? Right. So the cosine of pi over 6, well, let's see, that's going to be 1 plus 2 times. If I take the cosine of pi over 6, I get 1/2. So here, half of 2 is 1, plus 1 is 2. Oh, actually, I'm sorry. I was thinking of sine. Cosine is root 3 over 2. So here the 2's cancel out, and I get 1 plus root 3. Sorry about that. I was thinking about sine there for a second. Okay, 1 plus root 3. Let's see, pi over 4. That's going to be 1 plus 2 times the cosine of pi over 4. That's root 2 over 2. The 2's cancel out, and I get 1 plus root 2. Cosine of pi thirds, that's a half. So half of 2 is 1, plus 1 is 2. And then cosine of pi over 2, that's 0. So 1 plus 0 is just going to be 1. All right, so let me plot those. I'm going to come over here and I'm going to grab a polar graphing paper here. All right, so if my angle theta is equal to 0, my radius r will be 3. So on my paper, I'm going to go in the direction of the angle 0, and I'm going to go forward 3 steps. 1, 2, 3. Right about there. Now, so my graphing paper is in mostly in degrees. So let me put the radians in here. 30 degrees, that's pi over 6. This one's pi over 4. This one's pi over 3. And this one's already labeled as pi over 2. All right, so here we go. Pi over 6, I have 1 plus root 3. Root 3 is about 1.7. So adding 1 is about 2.7. So facing in this direction, I'm going to go forward 1, 2.7, almost all the way to the third ring. Here, if I'm facing in the direction of pi fourths, I'm going to go forward 1 plus root 2. Root 2 is about 1.4, plus 1 more is about 2.4. So if I'm facing this way, in the direction of pi fourths, I'm going to go forward 1, 2, and almost a half. 2.4, not quite 2.5. And then if I plug in pi thirds, I get 2. So if I'm going in the direction of pi thirds, I'm going to go forward 1, 2 steps like this. And finally, next, if I plug in pi halves, I get r equals 1. So here, if I'm going straight up in the direction of pi halves, I go up 1 step. Okay. I'm not done yet. I haven't finished my graph, but that's how much I have right now. And what I'm going to do is I'm going to go ahead and connect my dots so far. Okay. Now, one thing you'll notice is that there's a kind of direction to this graph. After all, angles have a conventional direction. You don't say 0 and pi over 6, pi over 4. No, you go this way. You go counterclockwise. So with angles, you have a kind of natural progression. You have a direction in which you're supposed to go in. Well, because those angles are ordered, that means that these points are ordered. Basically, you start with this one, then this one, then this one, then this one, then this one. So polar graphs have not just the individual points, they also have a concept of orientation. This graph starts from here and goes that way. So unlike graphs in rectangular coordinates, in polar coordinates, we have orientation. We have a direction that the graph's supposed to go in. It's different if it starts here and goes to the right versus starting here and going to the left. Even if it's the same curve, the direction is also part of the graph. So to highlight that, we're going to put a little arrow on these. That little arrow signifies, oh, this is the direction we're traveling in. Okay. So now, symmetry allows me to take this for granted. all these points that I have up here, I could just copy them down here. If I'm going 1.7 steps in the direction of pi over 6, then down here in the direction of negative pi over 6, I could go the same amount. It's just a reflection right there. Here, with this 1.4, I could reflect down to here. It's about 1.4. Here, this one, 2.4. Here, I'm on the second ring, so I could reflect that down to here, and again, I would be on the second ring. And here, I'm on the first ring, so I go straight down, and I'm on the first ring. So thanks to the symmetry that we established earlier, it's the same one we had earlier, right? And because the symmetry is with respect to the polar axis, to the x-axis, we can take this part for granted. We don't have to worry about these points. We know what happens. Oops. And it would help if I could draw straight. Something like that. Okay. All right, so now let's continue here. I've already gotten to pi over 2, but I still need some more over here. I don't know what's happening on this part. So let's continue with a little bit more. Theta and r. All right. Next angle, let's see, we'll do 2 pi thirds, and then 3 pi fourths, and then 5 pi sixths, and then 2 pi. And again, the reason I'm going with these is because they're the ones I know off the top of my head from the unit circle. We can use other ones, but these work just fine. All right, so this is going to be 1 plus 2 times. If I take the cosine of 2 pi thirds, that's going to be negative half. Like that. And so here, half of 2 is 1, but there's a negative there. So this is 1 plus negative 1. 1 minus 1, that's 0. Okay. The next one, I have 1 plus double. Oh, let's see, I've got 3 pi fourths. The cosine of 3 pi fourths, that's going to be negative root 2 over 2. Here the 2's will cancel, and I get 1 minus root 2. 1 minus root 2 is a negative number. Remember, square root of 2 is about 1.4. So 1 minus that is about negative 0.4, give or take. If you want to grab a calculator, of course, 1 minus square root of 2, that's about negative 0.4142. Oh, sorry, point. I forgot my decimal there, 0.4. 5 pi over 6. Okay, well, that's going to be 1 plus double. The cosine of 5 pi over 6 is going to be negative root 3 over 2. My 2's cancel out there, and I get 1 minus root 3, which that'll be a negative also. That'll be about negative 0.7. And again, you could grab a calculator if you like. 1 minus root 3. And again, that's about negative 0.7. And then for 2 pi, I get 1 plus double. Oh, sorry, not 2 pi, just pi. Nothing wrong with 2 pi, but that's a huge jump. On the unit circle, the next angle after 5 pi over 6 would just be pi. So here, the cosine of pi, that's negative 1. Like that. And that would give us, well, negative 2 plus 1 is negative 1. Like that. Okay, so let's see what happens when we plot those. Here we have negative distances, which sounds strange, but all that means is we're going backwards from the direction that we're facing. All right, so let's continue here. All right, so we've got, if we're facing, let's put our angles here. This one is 2 pi thirds, and this one is 3 pi fourths, and this one is 5 pi sixths, and then this one's pi. So if we're going this way, we're not actually going anywhere. We're at the origin. So from this point, we curved down to the origin. In polar coordinates, things are rarely straight lines. All right, we're going to continue following this pattern. So this is kind of a rounded shape. So we're going to continue here, and we're going to get to the origin. All right, if you're facing this way, you're going to go 0 steps forward. But we're going to follow this curve to get there. This is getting a little hard to see. Let me go ahead and adjust the camera. There we go. That's a little better. A little bit better there. Okay, so where were we? We were right here. So the next one, we're going to be going in the direction of 3 pi fourths, and we're going to go backwards 0.5. So even though we're facing this way, we're actually going to go this way. Going this way, we're going to go 0.4, about halfway to the first ring. A little bit less than that. Right about there. So following our pattern, it's going to go this way and continue up to this. If you're not certain, you're like, wait, how do I know it's going this way and not this way? You're going to continue following the pattern that we had before. Your graphs will rarely have abrupt changes. If that's still not clear, you're always free to plot more points than this. So you can plot something between 2 pi thirds and 3 pi fourths and plot those to try to get the pattern to be a little clearer to you. Here I'm doing just the ones that are simple because I know them off the unit circle. But you are welcome to plot more than this if it's hard for you to see with just the points that I have. Okay, if I'm going in the direction of 5 pi over 6, that's this way, but I'm going backwards. So I would end up going this way, and that would go this way 0.7. So about right here. And again, I'm following the direction, so it's looping back around this way. And then finally, if I am facing in the direction of the angle pi, well, I'm facing to the left, but since r is negative, I'm actually going to the right by 1. So going to the right to the first ring right there, and that connects my dot like this. But now, all of these pieces that I just found, I can take those for granted on the other side. So this part up here will now get reflected to down here. But now this part in blue that's down below the polar axis now gets reflected to be above the polar axis. And there's our graph. Our orientation continues this way. So it goes around. Usually just one little arrow is enough to signify the direction, but some people actually like to put a few more just to make it a little clearer. Oh yeah, I'm going this way, and then I'm going this way, and then I'm continuing this way, and this way, and this way. That's kind of overkill. You really don't need anywhere near that many. Just 1 or 2 are sufficient for pretty much any graph, but you can put multiple, as long as you have at least one showing the direction. All right, and this is the graph of our equation. What was our equation? I've already forgotten. It was r equals 1 plus 2 cosine of theta. So from this graph, we notice a few things. One, this could take a while. This wasn't even that complicated of a function. It's just cosine of theta plus a number. That doesn't seem that complicated. And yet it took a good 15 minutes to graph all that out. Let's see, about 12 minutes. It took about 12 minutes to graph all that out. So one thing is that this can take a while. Two, it was that this could have taken a lot longer if I hadn't taken advantage of symmetry. It took me that long to get just this part. This part didn't take me long at all because I could just take it for granted. Okay, so symmetry is helpful. But what if you don't have symmetry for a graph, right? Maybe not every graph will have symmetry. So does that mean some of them will be even longer? Yeah, that's exactly what it means. Some of these can take a really long time to graph if you're just plotting point by point by point, which is why we don't necessarily graph point by point by point. If you're running across a function and you have no idea what that is, you've never seen that before, you have no clue what it might look like, then you really don't have much of a choice. You're gonna plot it point by point. However, just like in algebra, there are some graphs that we know things about. If I ask you to graph a quadratic, you don't go in blind. You already know something about what the graph is going to look like. If I go back to my previous algebraic example, if I told you to graph this, you wouldn't plot 100 points to know what it is. You would say it's a quadratic, so I know it's a parabola. Even if you didn't know anything else, even if you didn't know where the vertex was or where the intercept was, just knowing it's a parabola is already helpful. Because if I have no idea what the graph looks like, I might need a dozen points to figure out, oh, it's kind of got this shape. But if I know it's a parabola, 3 or 4 points is enough for me to figure out where my parabola is going to be. So if I know something about the shape of the graph before I start graphing it, that will take a lot of effort, that will remove a lot of the effort necessary. Right? So here, let's go ahead and take a look at some basic graphs in polar coordinates. In rectangular coordinates, our basic graphs were things like lines and parabolas. Technically, sine and cosine functions are basic graphs in rectangular coordinates. We saw those in an earlier chapter. But now let's take a look at some basic graphs in polar coordinates. So the first one we're going to look at here is, oh, I guess I can zoom this back in, huh? All right, there we go. So the first of our basic graphs in polar coordinates is a circle. A circle that will touch the pole and will go out this way. Such a graph is made by having the equation r equals a cosine of theta. If you change this cosine to a sine, you still get a circle, but you get a circle that is touching here and going this way. So for cosine, it's going along the x-axis. The x-axis is cutting it in half. For sine, the y-axis is cutting it in half. So r equals a sine of theta. A here is some number, and that number tells you the diameter of your circle. So right here, this point is going to be a units away from the pole. Likewise, this point here will be a units away from your pole. A can be negative, but all that the negative does is if positive a goes this way, negative a must go this way. For this one, positive a is this side, negative a must be on this side. So a circle is one of the more basic graphs in polar coordinates. Okay? The next one we're going to look at is what's called a cardioid. Okay? Those are ones that look like this. Let's do r equals a plus or minus, doesn't matter which one, plus or minus, some number times the cosine of theta. Or, instead of cosine, you can use sine, a plus or minus a number times the sine of theta, like this. Now here, the graphs will look something like this. If you have cosine here, then your graph will point out something like this. So that the polar axis, so that the x-axis is cutting it in half. If you have sine, then it's going to look like this, where the y-axis is cutting it in half. This is called a cardioid, and the name's suggestive of a heart, which, of course, the image, that's what it looks like. It looks like the traditional cartoon heart. Okay? So this is a cardioid. This A and this B might be the same number, or they might be different. For the cardioid, you specifically need them to be the same number. You say, well, what if they're not the same number? Then we get a slightly modified cardioid. So that's going to be our next one here. If you have, it's going to be almost exactly the same thing. The graph will look almost exactly the same thing. In fact, the equation is exactly the same thing. Like this. Except now, we want our A to be less than B. Then we end up with what's called an inner loop lemicon. And an inner loop lemicon is actually what we graphed earlier. Right here. R equals 1 plus 2 cosine theta. That's going to follow this pattern. All right, 1 plus 2 cosine theta. Here the 2 is bigger than the 1. Here the B is bigger than the A. The A is less than the B. And we got this shape here. And in fact, that's what you're supposed to get. Here, your inner loop lemicon will look like a cardioid, except that instead of coming to a point at the origin, it'll actually loop around the origin slightly. Something like what we saw earlier. It'll have this little loop on the inside. And if it's cosine, again, the x-axis splits it in half. If it's sine, then the y-axis splits it in half. So something like this. There you go. Here, if you want to consider these as two separate graphs, of course you can, because they are labeled as two separate graphs. However, both of these are actually examples of lemicons. A cardioid is a lemicon that has a point on it, and a inner loop lemicon is a lemicon with an inner loop. Okay, so there's two kinds of lemicons. Well, actually, there's a third type. Here, if we have r equals a plus or minus b cosine of theta, or if you have r equals a plus or minus b sine theta, and if you have an a that is greater than b, then this is what's called a dimpled lemicon. So it'll look a lot like the cardioid, except that instead of coming to a point, it'll just kind of be slightly dented. So something like this. Like that. So it looks like the heart, but instead of coming to a point at the origin, it kind of starts to dip toward the origin, but it doesn't actually reach it. The amount of dip depends on the numbers. Sometimes it'll dip a lot, sometimes it'll dip a little bit, sometimes it'll be basically flat. It depends on the numbers themselves, but it won't come to a point the way a cardioid did. And again, for cosine, it is going to be split in half by the x-axis, by the polar axis. For sine, it'll be split in half by the y-axis. So something like this. Would be a dimpled lemicon. You may think of these as three separate kinds of graphs: cardioid, inner loop lemicons, and dimpled lemicons. But all three of these really are just one kind of graph. They're all just lemicons. You look at that and you say, well, that's kind of hard to remember. That's a lot of information. That's true. But every bit of information on here, if you remember every single thing, well, great, then you're done with your graph. But even if you remember some things, that makes the graph easier to work with. Over here, I may not remember what my vertex is. I may not remember my vertex formula. I may forget that I need to find my x-intercepts using the quadratic formula. But as long as I remember it's a parabola, I still save myself a lot of effort. And I'll know whether or not I'm right just by looking at the final graph I get. If I plot a bunch of points and I end up with something that looks like a J, that's probably not right. If I end up with something that looks like a V, that's probably not right either. I know what it's supposed to look like. With the graph that we made earlier, if we had created this knowing ahead of time that it was going to be some kind of heart shape, we probably wouldn't needed quite so many points. We could have done with maybe this one, this one, this one, and then that's it. And then the other half would have been automatic. So even if you don't remember every bit of information about these, even if you remember just, okay, number plus or minus numbers, sine or cosine is kind of heart-shaped, that's already a lot of effort. That's already a lot of effort saved when you create the graph. Okay. All right, so circles, lemicons, three varieties. The next type that we're going to look at is what's called a rose. And there's going to be roses are going to be separated into two different categories here, and it has to do with the number of of what we call petals. So let's see. If my equation looks like r equals a number times the cosine of another number times theta. Now this number has to be an integer. It has to be, in fact, a natural number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This can be whatever, but n stands for natural number. Okay. If you have r equals a cosine of n theta, depending on what n is equal to, and for now we're going to say n is going to be an odd number, this is what's called a rose. Okay. The roses, or sometimes called the rose curve, but I just know them as roses, is going to look like this. Okay. So when n is odd, what the n tells you is how many petals your graph will have. Here, we're going to start from the x-axis. This point that we're going to start from is a units away from the pole. So this number tells you how long the petal is. Now what you're going to do is you're going to imagine a circle. Now this circle isn't part of the graph, but just imagine it. In my case, since you can't see what I'm imagining, I'm going to draw it lightly in pencil. Okay. You're going to take that circle and you're going to divide it up into as many sections as this is as the number you have here. So for example, if n was equal to 3, in fact that's the one I'll do n equals to 3, then you would break this into 3 even sections. If this is 360 degrees, 360 divided by 3 is 120. So here you would say, okay, that's the 120, and then that's another 120 that gets me to 240, and then that's another 120 to get me to 360. Okay? So starting from the x-axis, you're going to divide that up into as many pieces as this has. Again, for the one I'm drawing, I'm saying n is equal to 3 for my example. And then what you would do is, starting from here, you would go up and toward the pole. Now from here, you're going to keep going in the same direction. You're going to still keep going sort of to the left and downwards. And you're going to keep going until you reach the end of the circle, because all the petals are going to have the same length. Now once you reach this point, you're going to double back. You're going to go back this way. You're going to pass back through the pole. Don't cross this line. Don't cross this line right here. You're just going to go straight back up, cross your pole, and go to the end of your third petal. Remember, each of these graphs has an orientation, so you do have to follow it in the right direction. So from here, go down, then back up, and then finally back down through the pole and back out to your starting point. And this is an example of a rose. In this case, it's specifically a 3-petaled rose. Okay, that's if you have a cosine there. What if you have a sine? Well, if you have r equals a sine of theta, or sorry, n theta, then that's going to be very similar. The big difference is where this petal starts. Here, the first petal that we started with started a units out on the x-axis. But if you have sine, it doesn't quite work that way. I'm still going to draw a circle of radius a. Again, that circle is not part of my graph, but it's going to be there to help me get the right size for my graph. Here, you should just imagine this. You're not actually going to draw it. Or if you do draw it, do it lightly in pencil so you can erase it at the end. What you're going to do here is you're going to say, okay, and I'll do the example again with an n equals 3. What you're going to do is you're going to take pi over 2 and divide it by this number. That will tell you it will tell you the direction of your first petal. So if I take pi over 2 and divide by, in my example I'm using 3, pi over 2 divided by 3 is pi over 6. That will be the direction of your first petal. So here, this angle, I'll call it alpha. Here, alpha is equal to pi over 2 divided by whatever your n was. Okay, so in our case, that's pi over 2 divided by 3 is pi over 6. And now you're going to do the same thing as over here. Now you're going to say, okay, that's pi over 6, or 30 degrees, whatever one you're doing. The degrees are radians. And then, again, you're going to split the circle up into 3 pieces. If that's one, each of those will have a measurement of 120 degrees. This is already 30, so adding another 20 will get me to 150. Adding another 120 will get me to 270. And there we go. So those will be my 3 petals. And again, the petals are going to be all the same length, and the length will be given by A. That's the radius of this outer circle. So to do that, we're going to start from the origin. This one starts from the middle here. You're going to go out to your first petal. You go out and then back. Keep going down and then back up and then out and then back in. My drawing's a little crooked, but these are all supposed to be the same length. And this would be another 3-petaled rose, but this time with sine instead of cosine. And if this is a 5 or a 7 or a 9, you would follow the same pattern. You would do the same thing, except here you would break this into 5 pieces, or 7 or 9, to get your odd-petaled rose. Okay, well, what if n is even? Okay, well, if n is even, let's see. Well, if n is odd, n is the number of petals. But if n is even, you need 2n to give you your number of petals. Okay, so and those are going to have the same equations. They're going to be r equals a cosine of n theta, and over here there will be r equals a sine of n theta. Like that. And for my example, I think I'll just use the number 2. So this is 2 for my example. And same thing for this one. All right, and the way the graphs of these look is like this. Once again, A is the length of each of your petals. So start by drawing a circle of radius A. All of your petals will have tips that end at that circle. That circle is not part of the graph, but it certainly helps us in making the graph. Okay, and that's our circle of radius A. Like that. Oh, and I realized I forgot my orientation on this one. It goes out and then in, and then down, and then back up, and then out, and then back in. Okay, so now if we have n equals 2, for cosine, we're going to, again, start on the x-axis. So here, this petal would start, let me use our red one here. My petal would start out here, and that's going to be the end of my first petal. And now I'm going to take double the number n. So if my n is 2, then the number of petals is actually 2 times 2, which is 4. So I'm going to split this into 4 equal parts. 1, 2, 3, 4. And my petals will be at the ends of those 4 parts. So now, starting from the x-axis, I'm going to go in and down, up and over. And again, the orientation is a part of the graph, so we do have to make sure we get that right. Then we go back in, up, and then finally back down and out. So starting from here, down, left, up, right. Like that. For a even petaled rose that has a sign here, you're going to have the same idea as over here. The first petal is what's going to change, and it's going to be at an angle. That's going to be pi over 2 divided by whatever your n is. So just like before. So here, if I call this the angle alpha, then my alpha is pi over 2 over whatever n is. Since my example is 2, I would have pi over 2 over 2, which is pi over 4 right there. So I would have my first petal there, and then again, break everything up into 4 equal pieces. So here, that's the first one. There's another one over here, one up here, and one down here. And if it was 6, you'd break it into 6 equal pieces, or 8, or 10, or 12, whatever even number you have. And now, you have, starting from this first petal, you're going to follow the same pattern. Toward the middle, down, back up and to the left, toward the middle, up, down, and to the right. It's going to follow that pattern. Over, down, back up, to the left, to the middle, to the top, and then down and close. And that would give us an even petaled rose with 4 petals when n was equal to 2. So again, you can think of these as different, but really they're just one type of graph, just different outcomes that you get from different specific numbers here. But really all of these can be thought of as what are called rose curves. So really we've got 3 types of graphs so far: circle, limicon, and rose curves. The next one is what's called a lemniscate, which is similar to a rose, except in a way simpler. So here, we're going to have r squared is equal to a squared cosine of 2 theta. So here it's specifically 2, not 4, 6, 3, not like a rose where you can pick different numbers. No, here this one's always 2. Or, of course, you can have r equals a squared sine of 2 theta. Like that. Either of those is going to be the same kind of graph. And this is what's called a... what's called a lemniscate. All right, so for a lemniscate, Notice that you have an r squared and an a squared here, cosine of 2 theta. So here these, and this should have a square as well. These are the ones that have squares in there. Okay, so those kind of stand out and are easier to notice that, oh yeah, it's one of the weird ones. Like this. Okay. And if you note that since there's not a lot of ambiguity here, you know that has to be the number 2, then there's a lot fewer details to remember about these. Lemniscates are going to graph as figure 8s. Once again, your A is going to be the furthest distance that you're going to get from your pole. So here I'm going to draw a circle of radius A. Same thing over here, I'll draw a circle of radius A. Those are not the graph, but those are going to be there to help me get the right size to the graph. Okay, so there's my A and there's my A. For r squared equals a squared cosine of 2 theta, you're going to make a figure 8 that's sideways, so kind of like the infinity symbol. It's going to start out here on the far right side. It's going to go in toward the middle, like that. And then we're going to continue this way. So it starts from here, kind of goes all the way to the left, and then it comes back all the way to the right. And here my graph is a little lopsided, but it is meant to be symmetric. The left side and the right side should look exactly the same, even though mine looks a little bit bigger over here. But it's a figure 8, or like an infinity symbol. For a lemniscate that has sine here instead of cosine, it's the same kind of graph, same figure 8, except instead of lining up along the x-axis, it lines up along this line right here. The diagonal line with the angle pi over 4, 45 degrees, however you want to say that. And again, same thing. It's going to come down, and then back up, and back up. And there we go. This is our lemniscate. Okay? Not much more to say about that one. And finally, the last one that we're going to have here is what's called a spiral. In particular, this one's called it's what's called Archimedes spiral, and it's probably the easiest one conceptually as well as computationally. R equals theta. That's it. That's the equation. This is a spiral. Oops, I don't know how to spell. Let's try that again. This is a spiral. And in a lot of books, it's specifically called Archimedes spiral. And, well, the name already tells you what it's going to look like. Here, you're going to start off at the pole when r is equal theta 0. And as theta gets bigger, as you go from 0 around this way, as long as your theta is increasing, your r is keeping up. So when theta is equal to 0, r is 0. When theta is equal to pi over 2, r is pi over 2. When theta is pi, r is pi. And it just kind of swings around and gets bigger off this way, like that. The orientation is the same as the orientation of the unit circle. That is to say, it's going counterclockwise. This is Archimedes spiral, and that's really all there is to say about that one. Oh, actually, there is one more thing to say. Unlike all the rest of the graphs we've seen, this one doesn't have a limit on its size here. These are all contained within a circle of radius a. Over here, all of these are contained within this one is a circle of diameter a, so it is contained within a circle of radius a. This one actually isn't contained within a circle of radius a, but it still doesn't go on forever. Right? The circle of radius a actually would not contain it, but it would still go out to a maximum size. So all of these eventually reach their maximum value of r, but this one just keeps on going. So here, it didn't stop there. It would just keep spiraling out and out forever. Okay? So although this might seem like a lot to remember, keep in mind that even if you don't remember all of it, even if you remember some of it, it still is helpful in creating a graph. So here, if you remember every detail about the different kinds of limicons, awesome. But if all you remember is, okay, r equals number plus or minus number cosine is some kind of heart shape, that's already a good start. You'll have fewer points to plot, and you'll know that you're correct or incorrect just by looking at your final results. Same thing for these. If you remember the details of the orientation, which way it's supposed to go, which way it lines up, how long the petals are, excellent. That's going to help a lot. But even if you just remember, okay, a times cosine of number theta is some kind of flowery looking thing, that already helps a lot. So as our last example for this section here, let's do one more graph. But instead of starting blind like we did for this one earlier, let's start with the knowledge of the types of graphs that we now can rely on. So let me go ahead and give one more example, and I think you guys should try this. Let's go ahead and graph, let's do this. We'll take r is equal to 2 plus 2 sine of theta. Okay. Go ahead and pause the video and give this a try. You're going to go ahead and graph this. You can, of course, graph it point by point by point, but that is kind of long and drawn out. It will get you the right answer eventually, but try to use other things that we've seen in this section. Try to see if you can test for the symmetry, see if that will get you anywhere, and see if you can remember something about the form of this. Even if you don't remember exactly the kind of shape that it would be, even if you kind of remember a little bit about it, anything you remember, any details are helpful. So pause this, do this to the best of your abilities, and then we will unpause. When you unpause, we'll go through this together. All right, so let's give this a try. I notice that I've got something that looks like r equals a number plus or minus a number times sine of theta. That's going to be one of the limicons. Now, I may or may not remember which one. Right? I remember there's something to do with those numbers. Is it dimpled? Is it the cardioid? Is it the looped one? Maybe I remember this is along the x-axis or the y-axis, or I may or may not remember a lot of this stuff, but I remember it's a limicon. And even with that little bit of information, that will already help me a lot on graphing this. Okay? So the first thing I want to do is I want to consider symmetries. Let me replace my theta with a negative theta. If I replace my r with a negative r, and if I replace both of those, theta and r, with negative theta and negative r, all three of those are going to give me a different test. So here, if I replace theta with minus theta, I get r equals 2 plus 2 sine of negative theta. And since sine is an odd function, the negative just gets factored out. So this becomes r equals 2 minus 2 sine of theta, which is different from what I started with. So this type of symmetry is not going to happen, meaning we will not have symmetry with respect to the x-axis. Okay. If we replace r with minus r, that's going to give me negative r equals 2 plus 2 sine of theta. Here our r stays exactly as it is. Our theta stays exactly as it is. So here we would have, well, nothing changes, right? Here, that's different from what we started with. If you try to get rid of the negative, you would multiply both sides by -1, and you would get r equals -2 minus 2 sine of theta. So here, with respect to the, which one's this one? We replaced r, so this one would be with respect to the origin, or sorry, the pole. We don't have that one. Well, actually, I guess I'm saying that wrong. It's not that we know we don't have it, it's that we don't know we have it. When you test for symmetry, having this not show up, like this fails, that doesn't mean the symmetry doesn't exist. It just means it might or might not. If this is equal to what we started with, then for sure we have that kind of symmetry. Here, since we do not end up with the same graph, with the same equation, maybe we have that kind of symmetry, but maybe we don't. So I guess I shouldn't say that we don't have it. It's more like we're not sure if we have it, so we can't take advantage of that. And then over here we'd have r and theta both replaced. So r equals, negative r equals 2 plus 2 sine of negative theta, which would give us negative r is equal to 2 minus 2 sine of theta, since the negative can be factored out. And again, that's different from what we started with. If you multiply both sides by a -1, you would get r equals -2 plus 2 sine of theta, which is almost the same, except that 2's got a negative on it. So here, with respect to the y-axis, we can't depend on that either. So when we finish the graph, we might find that we did have one or more of these, but the test failing here means that we can't rely on that. We can't actually know ahead of time that we have it. All right. So symmetry is not going to help us. Oh well, such is life. We still know that it's a limicon. We still have some ideas to what we have. All right, so let me grab my graph paper here, and let me start graphing a few things. Start with theta equals to, let me do it this way, theta and r. Okay, so theta is equal to 0. Okay, if we plug that in, sine of 0 is 0. 0 times 2 is still 0. So this is 2 plus 0, which is 2. Now, if I was graphing blindly and I didn't know anything, I would want to use as many points as possible. But here, since I already kind of know the shape, even though I don't remember a lot else about it, or at least I'm going to say I don't remember a lot else about it, I probably don't need every single angle. I probably don't need 30 and 45 and 60 and 90. So let me do every other one. I'm going to do pi over 4. I'm going to skip pi over 3. I'm going to go straight to pi over 4. I'm going to skip pi over 3 and pi over 6. And I'm going to use pi over 4 and pi over 2. So right away, I'm already cutting out half the information that I need. All right, so sine of pi over 4, that's root 2 divided by 2. But then times 2 will give me just root 2. So I get 2 plus root 2. That's about 3.4, more or less. 3.4. Sine of pi over 2, that is 1. 1 times 2 is 2, plus 2 more, which is 4. So if I'm facing this direction, in the direction of pi over 4, which is 45 degrees, pi over 4 radians, I'm going to go forward 1, 2, 3.4. So just about 3.5. If I'm facing straight up in the direction of pi over 2 radians, I'm going to go forward 4 steps. 1, 2, 3, 4. Okay. I never marked this one, did I? If I'm facing in the direction of the angle 0, which is directly to the right, then I would go forward 2 steps. So 1, 2. And I'm connecting my dots. Looks something like this. All right, let's continue here. A few more. Let me do, again, I'm going to skip over some points. I don't need every one since I kind of know what the shape is already. I'm going to go this way, and I'm going to skip over 2 pi thirds. I'm going to go directly to 3 pi fourths. So 3 pi fourths. The sine of 3 pi fourths, that's going to be root 2 over 2. But then times the 2 will give me just root 2. So I get 2 plus root 2. Which again is about 3.4, same as this one up here. And then let me jump directly to pi. I'm skipping over half of my angles that I would normally use. Sine of pi, that's 0. 0 times 2 is 0, so I get 2 plus 0, which is just 2. So if I'm facing this way, 135 degrees, that's the same as saying 3 pi fourths radians. I'm going to go forward, that's about 3.4, so 1, 2, 3.4, right about there. And then if I'm facing this way in the direction of the angle pi, I'm going to go forward 2 steps. 1, 2. It's going to look something like this. Okay. All right, then let's go ahead and plot some stuff down here. I've already gotten to pi. Let's do 5 pi over 4. And let's do 3 pi over 2. Okay. Sine of 5 pi over 4, that would give me negative root 2 over 2. So I have negative root 2 over 2 times 2. The 2's cancel out, and I just get negative root 2. So 2 minus root 2, that's about 2 minus 1.4, that's about 0.6. And then sine of 3 pi over 2, that's negative 1. Negative 1 times 2 is negative 2. So I have 2 plus a negative 2, 2 minus 2, that's 0. So if I'm facing this way, right here, to 225 degrees, that's the same as saying 5 pi fourths radians. We're going to go forward 0.6, so not even all the way to the first ring. Maybe right about here. And if I'm facing straight down, I don't go anywhere. I'm at the pole. Right there, since I already know what the graph's supposed to look like, it's supposed to look like kind of a heart shape. It's supposed to be a limicon. I can already take the last part for granted. I'm not even going to bother graphing this last part. If you can't see the pattern yet, of course, you are welcome to graph as many points as you need to. But here I'm going to take this last part for granted and say, okay, I know it's a cardioid, and cardioids have to be symmetric either left to right or top to bottom. Here, it's definitely not symmetric top to bottom. This is much bigger than this one, so it's got to be symmetric left to right. So here, even though we tested our symmetries and the symmetry tests all failed, this test failing doesn't mean you don't have that kind of symmetry. It just means you have proved that you have that kind of symmetry. But the graph actually did have symmetry with respect to this line, this y-axis. So here I'm going to have this last little piece here. And I'll draw it in red just to signify the fact that I was able to get that part without computing it. I was just able to take advantage of the fact that I knew it was a cardioid. And even though I did plot a few points, 1, 2, 3, 4, 5, 6, 7. That's definitely a lot shorter than it otherwise might have been, having graphed, by plotting every point on the unit circle, all 16 points. We were able to cut our information in half, and now here we can be fairly confident that this is the right answer, because it is a cardioid. If you flip it upside down, it actually does look like a heart shape. It is a cardioid, just as we would expect. So not only do we get done with it faster, but we're more confident that, yeah, that's almost certainly correct. So that is it for this section. That's it for this topic. This one does require a good amount of practice, so I would more than usual, I would suggest you try some of these after the lecture. Do as many of these as you can, and eventually you start seeing patterns. If you remember this information, it is extremely helpful. But even if you don't remember all of it, the more you remember, the better off you'll be. The less information you'll need to plot individual graphs, and the more confident you can be that when you have a graph, oh yeah, that's kind of what I expected. So you should be able to confirm or rework it as necessary. So that's it for this section. That's it for today. If you have any questions, comments, or problems, please reach out. Otherwise, I hope everyone has a good day.